Section 11.2, pressure. So jumping right in, the definition of pressure is the magnitude of the force acting perpendicular to the surface divided by the area A over which the force acts. So in short, we can write pressure, which is going to be noted with a capital P, as being equal to the force divided by the area. This is a really useful equation to hang on to and remember. And the SI unit for pressure is going to come from the unit of force, newtons, divided by the unit for area, which is meters squared, so newtons per meter squared, which is defined to be the Pascal, so 1 PA. So the Pascal, you know, is Newton per square meter. And that is our standard SI unit of pressure. Though we'll see there are some other units of pressure that will pop up quite a bit. So it's important to note this SI unit because it's different than some of the ones that you're presented with in the problems. So what does it actually mean, this idea of pressure? Well, it comes from the actual gas molecules themselves. The gas molecules, say within your tire, the air molecules, are all bouncing around. And as they bounce around, like bouncing into the walls of the tire, the fact that they're changing momentum means that they're exerting a force on the tire, and it's the tire is exerting a force on them, right? And so that outward force is actually what goes into the pressure. So we could imagine putting a little box in the midst of this tire, and it would feel this force from all sides because the molecules are everywhere. They're colliding with it from all sides. So it's always going perpendicular against any of the faces it's exposed to in terms of the force direction. And we could figure it out with so we could label one of these as a force arrow, right? We could focus in on that, say force 1. And then the area of interest would be the area of that square, which we could call A1. And so from that, if we knew the force and the area, we could calculate the pressure, for instance. Right, we're going to keep seeing a lot with pressure, so I think I'll leave the discussion there for now. And let's look at an example to be able to see a little bit more. So the force on a swimmer. Suppose the pressure acting on the back of a swimmer's hand is 1.2 times 10 to the 5th pascals. The surface area of the back of the hand is 8.4 times 10 to the minus 3rd meters squared. Determine the magnitude of the force that acts on it. Discuss the direction of the force. Right, so here we're just focused, it specifies on the back of the hand, this top part of the hand, and they give us that area, right? So that's really convenient. In this case, though, they don't give us the force, right? What do they give us instead? This is the pressure. And we instead need to find force. So how do we figure out force here? Well, we can go back to our pressure definition, because that's a really handy equation, as mentioned. So we have our pressure is equal to our force divided by the area, and we notice that we know the area, we know the pressure, we want to find the force, so we can just rearrange this equation to find our force. If we multiply both sides by the area, we get that the force is equal to the pressure times the area. So we're in really good shape to calculate that force. What about the direction of the force? Well, notice it's drawn down in the figure. Why is that? Well, that's because the force is always going to be acting perpendicular to the surface. So if the hand is flat, as shown in the figure, the force is going to have to be going straight down, perpendicular into that hand, right? If the hand was a different orientation, it would still be going in that different direction. Or if it asked about the bottom of the hand, in which case the pressure is probably about the same on the bottom. So it's a probably fairly similar force, slightly more we'll see below. But in that case, the force would be directed upward. So that gives you some idea. We can plug in those numbers. So we get force is pressure times area. So it comes out to a force of 1,000 newtons, or with 2 sig figs, 1.0 times 10 to the third newtons. So since the water pushes perpendicularly against the back of the hand, the force is directed downward, right? But the forces are on all sides of a person in the water, right? You're always getting pressed in by the water around you. And it turns out you also have pressure all around you, even when you're not in the swimming pool. So pressure exists even just from air. This is something known as atmospheric pressure. Atmospheric pressure at sea level is 1.013 times 10 to the 5th pascals is equal to 1 atmosphere. This is a really, really handy relationship. 1 atmosphere is a pressure, another unit of pressure that's often used, and it's abbreviated to 1 atm. Atm is atmospheres. And the reason it pops up as a unit is because it tells you the standard pressure. So if the pressure isn't specified, it just says that you're outside on Earth, you can know that the default pressure is 1 atmosphere, which in SI units is 1.013 times 10 to the 5th pascals. So keep this relationship in mind because it pops up quite a bit. And this is all around us, which means we feel a force from all sides from this atmospheric pressure. Well, how much force? Well, that's going to depend on the area, right? If we looked at base of this area, where the area base is 1 meter squared, well, then if we wanted to find the amount of force from that, we'd find that it's equal to 1.013 times 10 to the 5th newtons, a huge amount of force. Why don't we feel that force? Well, because it's all around us, right? We're acclimated to that pressure around us. But we can see that force in action if, for instance, you have a can and you remove the atmospheric pressure inside the empty can, right? The can normally would have atmospheric pressure outside and inside, but if you suck all the air out of the inside, now the atmospheric pressure is going to push from the outside and it will crush the can. Another place that this pops up is actually not just physics experiments, but with tankers. So this can happen just with routine cleaning it. So they clean it out they have boiling water in there. And what they're supposed to do is leave the valves open as it cools overnight. But if by chance you have the boiling water inside and then you close the valves, then overnight it starts to cool down. And as the gas cools, the pressure drops inside the tanker. And then the atmospheric pressure can win, right? There's no outside forces on this. It's just a drop in pressure inside. And it can destroy this giant metal tank. So atmospheric pressure is really impressive. It can be a huge amount of force there. We just take it for granted every day. But you can know that you're getting through a huge amount of pressure around you. So I'm proud of you for facing that, and hang in there. All right, we will wrap up this section right there.